All right. We are going to talk about the TestNav 8 questions for the Algebra 2 SOL. We're picking up at question 24. Graph of f is shown below. They even give us the function x times x plus 3 times x minus 5 all over 9. So we don't have to put this into Desmos. It's going to show us anyway. So it says, what is the value of the apparent minimum in the interval -3 to 6? So I'm just going to come to my graph here, and I'm going to start at -3, which is right here. And I'm going to go all the way to 6, which is right here. So I'm just looking in this window right here. Just in this window, what is the apparent minimum? Minimum would be happening right about here or at -4. So at -4, we have our apparent minimum. Why apparent? Well, because technically, if we look outside of our window, we do approach -infinity. So for right now, we're dealing with just our minimum right here, -4. The next question, throughout which interval is the following function increasing? Now, there is no graph. So the first thing I'm going to do is come to Desmos. And I'm going to type in my graph, -x cubed plus squared plus 4x minus 2. And you can put a y equals out front if you feel like it. Ooh, sorry. Well, doesn't really change anything. So where are we increasing? Well, increasing means you have a positive slope. So if I'm looking kind of at my turning points here, we've got one right here, -x cubed plus 2x squared plus 4x minus 2. And so what we're dealing with here is we're looking at this interval right here. So I'm just going to sketch it on my paper so we can kind of deal with it. We've got down to here and then down. So it's something like this. We've got -0.667, comma -3.48. And then up here, we've got 2, 6. And where we're increasing is right here. So we're increasing from -2/3 all the way to the number 2. So if we want to look at our answer choices, we are not increasing from -infinity to -3. That would be somewhere in here. This is not an answer choice. Are we increasing from -3 to 0? Well, -3 is over here somewhere. We are not increasing. From 2 to infinity, are we increasing? No. Really what we're looking at is this as our only option. Between 0, which happens right about here, to the number 2, we're increasing. Okay, so process of elimination, get our answer. Number 4 asks us, what is the 0 of g of x equals 9 to the x minus 243? Just a quick reminder that the word 0 has a couple meanings. It also means solution, which also implies x-intercepts, which also is going to imply factors and so on and so forth. When we see 0, we can be thinking and knowing all of these different things. Now, we are dealing with an exponential function, 9 to the x minus 243. And so what we can do is set it equal to 0, because that's what a 0 is. Where is my graph going to be 0? So I'm just going to add 243 to both sides. And I want to get x by itself, but the only way to get x by itself is to take this exponent and take the log base 9 of both sides. Because a log base 9 and a base 9 are going to cancel out. I'm left with an x, and I'm going to come to Desmos, and I'm going to go to functions, miscellaneous, log with the little a, so I can type in my base 9 of 243. And that is 2.5, or if we want a fraction, 5/2. Now it doesn't say what to leave my answer in, so we're going to just kind of leave it like that. We're going to write 2.5, but we're also going to have, just in case you wanted to know, it is 5/2. How many and y-intercepts does the following graph have? Again, there is no graph that's here, so what I'm going to do is type that into our Desmos and get a picture. Okay, so we're going to go here, y equals x plus 1 over x. So I've got a picture, and I want to know x-intercept. So it looks like the only place it intercepts is right here, -1, 0. So we've got 1 x-intercept. And if we're looking for a y-intercept, let's see, does it cross my y-axis? Cross my y-axis. Doesn't look like it's crossing my y-axis. I'm all the way down here in the 30s. Okay. What about up here? Does it cross my x-axis or my y-axis up here? Super, super close. Again, I'm in my 30s. Is it going to cross my y-axis? No. Looks like we're dealing with a y equals 0. Or an x equals 0 asymptote. So we have no y-intercept. So just one x-intercept. It happens to be at -1, 0, and no y-intercept. Again, number 5. Which of the following describes the end behavior of this function as x approaches -infinity? X is approaching -infinity. We want to know what's happening at the end of our graph. So we're going to come here to Desmos, and we're going to type in our function because there is no picture for us. We're going to do x minus 6 all over x squared. Okay. And we are worried about what's happening as x gets closer and closer to -infinity. What is happening? Well, my y values are getting closer and closer and closer to my y-axis. They're not going to cross my y-axis, but they're getting super close to that y-axis. They're not crossing my y-axis and continuing on to infinity. They're just slowly approaching 0. So if I'm looking at my answer choices, y approaching 0 is an option. 6, similarly, is asking about end behavior as your x approaches 0. This is a log function, so it's going to look a little different. There's no graph, so I'm coming to Desmos, and I'm going to type in 9 log of 2/5 x plus 5. I'm just going to zoom out a little bit. What is happening as my x is getting closer to 0? Because if you notice, there's no x values in the negative side here, right? So as my x is getting closer and closer and closer to 0, what's happening? Well, my graph is going down, and my y is going to be approaching -infinity. So as my x gets closer to 0, my graph is headed downwards towards -infinity. Again, end behavior of graphs. For number 7, it says identify the equation of the horizontal asymptote. Horizontal is this direction, and it is a y equals some number. Vertical asymptote would be up and down, and that would be an x equals a number. So we want to make sure we drag and drop the correct answer choices into the correct boxes. There is no graph for this provided, so we're going to come to Desmos and graph this. So we've got y equals, got 4x plus 1 in the numerator, and we have x minus 3 in the denominator. Okay, and so what we're looking at here, where would my asymptote be looking like? We could always just type in our answer choices. So if this was multiple choice, we could type in y equals 3. And we could see, not quite, my asymptote's intersecting that line. So what if we pick 4? 4 is looking a little better, right? It's approaching on both sides there. So y equals 4 would be one of my asymptotes. Okay, if we picked x equals -1, that is on the asymptote. It's intersecting my function right here. So what if we picked, I don't know, 2? Again, looks pretty good, but crosses my function. So maybe not 2. What about 3? 3 look good. 3. There we go. So my two asymptotes here are y equals 4 and x equals 3. Number 8 says, which of the following is the inverse of this function? When we studied inverse, we created an inverse by first writing it as y equals, and then switching the x and the y. So my x comes here and my y comes here. Now I just solve for y. So I would add 8 to both sides. And then to undo a cube, I would take the cube root of both sides. So I would have these cancel out, and I've got y equals the cubed root of x plus 8. Now this is my inverse, so I do have to notate that I found y to the -1. And now I'm just looking at my answer choices. And inverse. For 9, this is composition of functions. If you have g of x be 2x minus 5 and h of x be x of 3 minus 7, they want you to compose g of h of 12. Now, we deal with this kind of as a layer, and we're going to deal with the inside layer first. We're going to find just h of 12. So we're coming here to our h function. We're plugging in the number 12 where we see x, and we're going from there. So we've got h of 12, 12 divided by 3. 4 minus 7 is a -3. So where we know h of 12, we know that it's -3. So really, what we're dealing with now is our outside, our g function. We're going to plug in what we got for our h of 12. So I'm coming to my g function, and everywhere I see an x, I'm going to plug in -3. So we're going to say 2 times -3 squared minus 5. Well, that would be a 9 times 2 would be 18. Final answer would be the number 13. Start from the inside, work your way out. Number 10 says which graph represents f of g of x. So we're going to take g of x and we're going to plug it into our f of x. So we are taking this and plugging it into that x function there. So we've got our x minus 1, and what we're plugging in there is the g function. Okay, well now all we have to do is simplify. Our combining like terms, -2x doesn't have any like terms, 4 minus 1 is a -3. And then all I need to figure out is which one of these graphs is the -2x minus 3. Well, it's not going to be this. This is a parabola. It's an x squared function. This is rational. This would be like x over something. and it's not going to be these two. So already we're eliminating these two as possibilities. Not going to happen. So which one of these graphs has a slope of -2 and intercepts at -3? So come here, just in case you're having a brain fart moment, you can't remember how to graph this line. -2x, I'm sorry, that should be a +3. That would be graph A, because it intersects at -3 and it has a down 2/1 slope. Number 11, we see our vocabulary word zeros again. The zeros of the cubic function are -1, -2/3, and 5. Zeros simply mean solutions, which then help us get factors, which is what we're dealing with in this question. How do we take a -1 and turn it into a factor? We simply change the sign. So a -1, the factor would be x plus 1. For our -2/3, we would have x plus 2/3. For our 5, we would have x minus 5. So already we're seeing this is our answer choice. We're seeing this is our answer choice, and we can go ahead and eliminate these here. Now, if you notice, there isn't any term that says x plus 2/3. Well, that's because one way to get 2/3 is to have it just x plus 2/3 equals 0. Or you can take the denominator and put it in front of your variable. As this is a negative, my factor must be a plus. So I can eliminate this option right here. And I'm really only left with this third one. Ta-da! Next, the volume of a container varies jointly with the square of its radius and its height. Let's pause and talk about what it means to vary jointly. Varying means it's related. It's going to have a variation, a function. It's going to depend on the square of a radius, or r squared, and the height. Jointly just means together. So my volume is going to vary the square of the radius and the height. That's all I'm going to set up with that first sentence. Now it's going to give me some information. It's going to say the height of my container is 10 centimeters. It's going to say the radius of my container is 6 centimeters. And it's going to say my volume is 377 cubic centimeters. It wants to know what the volume of a container with a radius of 4. Now, it says it varies with my radius squared and my height. But there's always room for some number, some constant, k, to vary. Because 2, if it's constant, doesn't affect how I'm varying. So we're always going to have a k right here. What we can do is figure out what that k equals, because we have volume, we have radius, and we have height. What we don't have is this constant k, but we could find it. Let's just type that into Desmos, see what happens. 377 equals x times 6 squared times 10. My variation is 1.047. So my constant, 1.047. Now, it wants to know a new volume. So I have to use the same formula, but this time I know my constant. This time I know my constant is 1.047 radius squared height. It tells me my new radius is 4. It tells me my new height is 4. And they want me to round to the nearest whole number what this new volume is going to be. So come over here and we're going to say, okay, what is 1.047? 4 squared times 4. 6.8, which if I round to the nearest whole number is just 67. One of our favorite types of questions on the SOL is dealing with data. And so we're going to start talking about data. The amount of lost revenue from tickets not sold for a concert is shown below, with the ticket prices that include tax. What equation best models the relationship between Y, the revenue that was lost, and X, the price of the tickets? So I'm not really worried about the number of tickets that were not sold. What I'm worried about here is my Y and my X values. They are what I'm looking for. So I'm going to go straight to Desmos and I'm going to create this table with X's and Y's. So come here to my plus sign, create this little table, and my X values are 25, 35, 55, and 125. My revenue lost was 2,100, 2,800, 50, 60, and 40,325. And if I can't see my data points, I can always hit zoom fit, and it's going to go ahead and do this lovely curve for me. Now, this curve right here tells me that it's not going to be just a linear best fit. So it's not going to be a curve of best fit that's going to be Y1 is approximately MX1 plus B, right? If I kind of zoom out here, this is not fitting my data super well. So I don't like this one. However, maybe a curve like a X1 squared plus VX1 plus C. Maybe something a little more like this. Aha, look at that. That looks very nice. That is looking a whole lot better. So my line of best fit is going to be probably that quadratic, which we type in to Desmos like this. And then when we fill out our answer, we have to actually use the data that they've given us, okay? So we're actually gonna fill in the A, the B, and the C. So we're gonna say Y equals our A, which was 4.04 X squared, plus our B, which was negative 227. X plus your final answer is going to look something like that. For the next question, we are dealing with normally distributed data about rainfalls in 32 cities. It gives us the mean, which is kind of an important piece of information right here, the mean, and it gives us the standard deviation, and it gives us a histogram. We talked about a histogram being frequency, how often things happen. It says identify each interval that may have data points within 1.5 standard deviations. So remember when we create our little bell curve here, we say our mean is in the middle, 32.5. 32.5 is actually kind of right in here on our histogram. So one standard deviation away, we're going to subtract 4 inches, or we're going to add 4 inches. That's one standard deviation away. So that would be 28.5, or 36.5. Again, 28.5 is happening somewhere in here, and 36.5 is happening something in here. So far, data that's going to be between the first deviations, this one, and this one, for sure. Now, we only want to go a half more deviation. If 4 is a full deviation, then 2 is a half deviation. So we're looking at 26.5, right? 26.5 is somewhere in here. And a half more deviation would be a 38.5. So we're looking at something kind of like right in here. So we're going to select these as well. Those are all of the columns that have data points between the first 1.5 standard deviations from the mean. Keeping along that same theme, we're talking about normally distributed data. The heights of 200 kindergartners are normally distributed, and we have a mean of 400, a standard deviation of 1.8. Approximately how many students have a height between 37.3 and 445.5? So we can do this one of two ways. We could draw our lovely table, we could keep going, or we could come to Desmos because we love Desmos. It can help us figure this out. We come to function distributions because we have a normally distributed data. And then we type in our mean, which is 40. We type in our standard deviation, which is 1.8. And then we hit zoom fit because we want to see this data. Now we want to find the probability that someone is between 37.3 and 44.5. And we get 92.69. So we have about 92.69% of our students are between those two heights, 37.3 and 44.5. Now that's percent. That is not how many students we have. We want 92.69% of how many students are in this school, 200. And so we've got about 185.4. Your answer's got to be a whole number. So let's stick with 185 students because you can't have 0.38 of a student. (92.69% of 200 students. Similar, a normally distributed set of 968 values has a mean of 108, standard deviation of 11. What is closest to the number of values expected to be above 125? So we've got our lovely bell curve. We have our mean in the middle of 108, standard deviation of 11. So if I add 11, we're going to get 119. If I add another 11, you get 130, keep going, etc. 125 is between our standard deviations. So our best bet is to come here and to ask Desmos. Our mean is 108. Our standard deviation is 11. And so we're going to need to fix our zoom. And we want to know that what is the probability that things are above 125? To be above 125, we're making 125 our minimum. And so we're going to say about 0.6, or sorry, we're going to get 0.061, or if you want that as percent, 6.1% of our 968 data values. So we're going to do 6.1% of our 968 data values. So it's about 59 data values are expected to be above that, about above 125. Base set, normally distributed. Typo, supposed to be with a mean of 68.42, standard deviation of 7.91, and an element in that set is 57. It wants to know what the z-score is for 57. Now, there is a formula on your formula sheet for z-score. It is to take that data element, to subtract the mean, and then divide by your standard deviation. Well, what's my data element? It's a 57. What's my mean? It's 68.42. And what was my standard deviation? It was 7.91. So my z-score for this data point at 57 is going to be 7 minus 67.42. And we have to divide all of this by 7.91. It's going to be negative 1.3173, blah, dot, 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 dot. And it says to round to the nearest hundredth. Hundredth means second place. So this has got to go up to a 2, negative 1.32. That is my z-score. Number 18, a store owner employs a total of 3 cashiers and 7 clerks. The owner plans to collect a committee of 1 cashier and 2 clerks. What is the number of different committees the owner could choose? So we have 2 different categories. We have cashiers and we have clerks. Does it matter what order we choose the cashier and clerks in? Not really. It doesn't matter. But we do have 3 total cashiers and we need to choose one of them. So we're going to choose one because the order we choose these cashiers in doesn't matter. We have 7 total clerks and we need to choose 2 of them. So what we're doing here is choosing. We are choosing. Something that gave that away was the word choose. And then choose. It is a formula on your formula sheet, or we can just come to functions, hit stats, and we've got our n choose r. We've got our 3 choose 1. We have our 7 choose 2. So 3 different ways we can choose the cashiers, 21 different ways we can choose the clerks, for a total of 63 different ways we could choose a committee that has 1 cashier and 2 clerks. I'm going to skip 19 and come back to it in a second. For a family reunion planning committee with 8 members, they plan to elect 3 officers, a president, a treasurer, and a historian. Does the order matter? Yeah, it matters if you're a president versus a treasurer versus a historian. You will have very different jobs. So the order does matter, making this a permutation. This is a permutation because the order matters. We like to think of this as positions. If there's positions that you're filling, that's a permutation. There were 8 total people that we could choose from, and there are 3 offices that we can put them into. How many different ways can we fill them? We're going to use permutation instead of the combination. So functions, we're going to pick NPR. 8 total people, 3 positions that we're filling. So there are 336 different ways we can fill those positions. Back to number 19. 19 shows us a table that has money raised during a fundraiser from 4 different classes, and they've just picked 1 student from that class to be represented. The data has been normally distributed. So what we need to do is figure out which of the 4 students raised the greatest amount of money. If you notice, the mean, the average for each class is different. The standard deviation for those classes is different. And where that student lives in the z-score is also different. What we're looking for is how much money did Jill actually raise? We don't have a dollar amount. But what we could do is take her z-score and say this is supposed to be whatever her dollar amount is minus the mean divided by her standard deviation. Kelly's dollar amount is whatever her z-score is going to be the money she raised minus the mean for her class divided by the standard deviation. You get the picture. We're going to take each z-score and we're going to use our z-score formula to figure out what actually was the amount of money each of these students raised. So, to Desmos, we're going to ask, all right, if we have 1.8, and we need to figure out how much money this person raised, factor the mean, divide by the standard deviation, and we get about $80. So this first one, 79.8. So Jill raised $9.8. Has a different z-score. 2.1 x minus her mean, which is 58. Standard deviation. She raised more money. 83.2. So far, Kelly has raised the most money. 1.4. Monroe has raised the least amount of money. And let's check Tim. 2.5 x minus 57. And Tim just didn't have enough. His was 82 even. So Kelly was the one who raised the most money. She raised $83.20. Last question. If we're looking at students' scores on this graph, it summarizes over 50,000 students' data test scores. The data is normally distributed. Your mean is 81. So right here in the middle, you've got 81. Your standard deviation is 2.5. Ends under the curve where only the data for approximately 23,750 students are located. Well, if we're only looking for 23,750 students and there were 50,000 students total, what percent am I looking for? What percent am I looking for? Let's just ask Desmos real quick. Hey, we take 23,750 and we divide that by 50,000. We're looking for about 47.5%. 7.5% of your data. Now remember, this is 13.6. This is 2.2. This is 0.1. Out because it doesn't say that the scores have to be bigger than the mean, less than the mean, etc. They've just got to be a number. If we add 13.6, 2.2, 0.1, all of these numbers up, we're going to get enough. Those are 34.1. There's 47.7. What if we picked? That's not enough. That's too much. So it looks like we need to select a 34.1 and a 13.6. That means we can select a region 5 and a region 6 together. We can select a region 4 and a region 3 together. As long as we're selecting a region that's going to add up to 47.5% of my data, I'm going to be comfortable.